I'm Bob Duhamel, and today we are going to take a closer look at conductors, insulators, and semiconductors. What makes a particular material a good conductor depends on how the electrons bond to a mass of that material. And most metals are good conductors. Let's take a look at how metals are made and why they are good conductors. We'll start by taking a look at a hydrogen atom. A hydrogen atom consists of a single proton, which we will show as a positively charged circle. And this positive charge will tend to attract electrons. And if an electron comes by and has a low enough energy level, it can be captured and that electron will orbit around that proton. I'll show the electron as a little circle with a minus sign in it. Now this is the Rutherford-Bohr model of the atom, and it's not quite accurate, but it's good for modeling how atoms act. In reality, the electrons kind of form a cloud around the nucleus, and their average energy is represented by the orbital level I show here. The orbits are not quite as clean, but we'll show the Rutherford-Bohr model just because it is easy to use to illustrate how these atoms act. So here is a hydrogen atom, a single proton with a single electron orbiting around it. Now if we do some nuclear fusion and bond two protons together, we now have a helium nucleus here. Now helium will normally have two neutrons around it, but just to simplify things, we'll leave the neutrons out. And this two protons have enough of a positive charge that they will attract two electrons, assuming the electrons have a low enough energy level that they can be captured. So a helium atom will have two electrons around it under normal temperatures and pressures, and those two electrons will be at the same orbital energy, or show them as a certain height of orbit in the Rutherford-Bohr model. Now if we do some more nuclear fission or fusion and end up with a lithium atom, that will have three protons. Now the difference in the lithium atom is that by the quantum nature of physics and way things work, is that we cannot have any more electrons with this amount of energy around the nucleus. We can only have two at this lowest level of energy. So if this lithium atom captures an electron, it can capture a higher energy electron, and if it does, that electron will be in a higher orbit around the nucleus. So what we have is the outermost shell, as they call them. We call the orbits of these electrons a shell because, well, it forms really a cloud, but since the electron is not in a nice clean orbit like the orbit of the moon around the Earth, it's more chaotic and goes around and it eventually describes a sphere, at least the energy does. We call that an orbital shell because it's like there's a shell of electron orbit here and another shell here. So we have two shells of electron orbit. This outer shell is called the valence shell. And the nature of the valence shell, mainly how many electrons are in it, are what determines most of the chemical and electrical properties of that material. And if this valence shell has three or fewer electrons in it, we have what's called a metal. So lithium is a metal. Now we also saw hydrogen. Well, hydrogen only had one electron. In fact, it only had as many as helium had two. Does that make them metals? Sometimes. Sometimes hydrogen acts like a metal, sometimes it doesn't. But for right now, let's look at lithium as the first metal. One thing about this valence shell, the fewer electrons it has, the easier it is to add energy to that electron and cause it to break away and float away freely. So we can add just a little bit of energy to this and it will escape. Now if we make a mass of lithium metal, we end up with a whole bunch of lithium atoms. I'll just draw them as circles. And each one of those lithium atoms has one electron in its valence shell. Just draw these as little dots here. Now it's the nature of the bond that these metals make. What metals do is they make what's called a metallic bond. And the nature of that metallic bond is that the outermost layer of electrons, the valence shell, does not fit into the crystal structure. So the amount of energy they have causes them to move freely about that mass of metal. So these electrons in this mass of lithium can float around and go any direction they want. They can go this way, they can go that way, up, down, whatever. They can drift around just like the air in this room can drift around, as long as some of the air that moves to the back of the room is replaced by air that comes to the front of the room, and the air molecules stay evenly dispersed in the room, then everything is equalized and we have an equal pressure through the room. Same thing happens in a mass of metal with the electrons. They can float around freely as long as if a few electrons float this way, then some other electrons have to float the opposite way to take their place so that the electrons stay evenly distributed, and so that each atom in this mass of lithium or whatever metal we have has basically one electron nearby it, so they're all evenly dispersed throughout the metal. So now if we take a look at this mass of lithium as a block of lithium metal, well, there are gazillions of free electrons that are free to move about inside this. And so if we put a battery across this such that it's positive on this side and negative on that side, that's going to tend to push the electrons in this direction. And the nature of this is that since we have a battery out here, there's the negative side, positive side, as electrons move to this side, they will be sucked up by the battery just like a vacuum cleaner, but also like a vacuum cleaner, they will be blown back out this side and come back to just circulate around and round. Now, of course, the electrons that are coming out of the negative side of the battery are not the same ones coming in the positive side, but for all intents and purposes, it looks like they are. And so just like a vacuum cleaner, which has one side that sucks and the other side that blows, a battery works the same way. So by hooking up this battery to this block of metal, we get electrons pushed in this way, sucked out this way, and we get a current flow through that metal. And it's because of the electrons in that valence shell can move freely around that we can push the electrons freely through this metal. Now if we go back to our nuclear fusion and make the next element in the tables by fusing another proton in here, we get an element called beryllium. There will be 2 electrons in the lower orbit and 2 electrons in the next higher orbit. So now there's 2 electrons in the valence shell, and beryllium does not conduct as well as lithium, because the more electrons we put in the valence shell, the more or the less able they are to move inside that mass of material. And the next one we add to here would be boron, so we add another proton, and then that adds another electron, and that becomes boron, which is an even less conductor than beryllium is. And let's add one more electron. This makes carbon, and carbon has 4 electrons in the valence shell. And we no longer have a conductor because, like I said, or we no longer have a metal. We no longer have a conductor because the metals, and thus the conductors, have 3 or fewer electrons in the valence shell. And now we have what's called a semiconductor. We'll talk about those more at another time because they're very special in the way they work. But a crystal of semiconductor is essentially an insulator. It does not conduct very well at all. They say, well, they conduct better than insulators, but not as well as conductors. In reality, they're pretty poor conductors. But by putting impurities into crystals of semiconductors, we can control their conductivity in very special ways. We'll talk about in much more detail later, because semiconductors are what all of our modern electronics are made from. So after carbon comes nitrogen, which has 5 electrons and even less conductivity. Then after nitrogen comes oxygen, and then after oxygen comes fluorine. And fluorine has 7 electrons in its valence shell. and it is a very poor conductor. Now, if we were getting into chemistry, we could talk about how special fluorine and chlorine and its relatives are. They're extremely reactive chemically, but we're not too interested in what they do electronically or electrically, so we're not going to get into that at this point because this is not a chemistry class. But if we continue on, the next material is neon, and that has 8 electrons in the valence shell, and anything with 8 electrons in the valence shell is very non-reactive, very non-conductive. They don't even form very good molecules. They tend to make single atoms that float around. They have special properties of their own, but once again, electrical properties we're not too interested in. But we're interested in what happens next. So we have our neon, and we're going to add one more proton to this nucleus, and now we get sodium. Now, the most electrons we can have in this next shell is 8. So that means that the next electron that's attracted to this atom is going to be in another even higher shell. And being even further from the nucleus, it takes even less energy to kick this electron out. So we find that sodium is an even better conductor than lithium was. And so there's our one electron. And so now we have sodium. Now, why don't we use lithium and sodium for wires? Well, it's because they're extremely reactive. If you ever manage to get a hold of some lithium, it's going to be in a vial full of oil or something to keep air away from it. Air and water react with them very violently. We don't want to be playing around with those. But that's sodium by itself. Of course, we know that if we mix sodium and chlorine together, they react and produce sodium chloride or table salt. But once again, that's not too interesting electronically. So there's our sodium. The next thing we get if we add another electron is magnesium, which has 2 electrons. So magnesium does not conduct quite as well as sodium. After magnesium comes another proton, another electron. We have aluminum. Now, aluminum is not going to conduct as well as magnesium or lithium because it has 3 electrons. But aluminum is so abundant and is a decent conductor that it is a very popular material for certain types of conductors. Now, most of the conductors you have, such as in your house, they were using aluminum wiring at one time, and it turned out to be problematic for house wiring. But the reason was that the way house wires are connected by compression connections, such as a screw going into the wire and making a good solid connection just by the pressure, tends not to work that well with aluminum, and it would start to create more and more resistance. Current through resistance, what does that cause? Heat. And I had a few houses burned down. I don't know if aluminum wire is used anymore at all. I'm not an electrician, but copper wire is the wire of choice for houses. But how about long distance wires, things that go perhaps from Hoover Dam to Los Angeles? Copper would be too expensive to go those kinds of distances, but aluminum isn't. So aluminum is very popular for large wires going long distances and where lots of wire is needed. Even though it's not as good a conductor as copper is, it's good enough and it's cheap. So your long distance wires tend to be a iron core, or should I say steel core, wrapped with aluminum wires to carry electricity long distance because it's a good enough conductor and it's cheap. So there's our first important conductor, which is aluminum. If we keep on going, we add more and more protons, which add more and more electrons. And the next important metal we get to, already mentioned, is copper. So I'll just draw our core, which is called the kernel of the atom. This would be the nucleus plus all of the shells of electrons minus the valence shell is called the kernel. And so here is a kernel of copper with its 1 electron in its valence shell. And copper is a very good conductor. It's kind of in that sweet spot where copper, gold, and silver have just the right amount of protons in their core that they don't have so many that they start making the conductivity less, but not as many as others. So there's a sweet spot in the, if you look at the periodic table, you'll find that copper, gold, and silver are all in the same column, and they're our best conductors. So copper, although it's not the best conductor there is, the cost versus conductivity makes it probably the best we can get. Gold is a better conductor, silver is also a better conductor, but those are ridiculously expensive, or prohibitively expensive, so our most common conductor is copper, which is kind of expensive in its own right, which is why for long distances and big massive conductors we might use aluminum, but for the most part we use copper where we can. And copper once again has a single valence electron, and so when we have a mass of copper, for each copper atom there's one electron that's free to float around, and that's what makes copper a good conductor. Okay, so our conductors tend to be metals, because metals by definition have either 1, 2, or 3 electrons in the outer shell, or the valence shell. And when we have 1, 2, or 3 electrons in the valence shell, it's very easy to impart enough energy that they will break free and float around in a mass of that particular type of material. So that's what conductors are. Now let's look a little more at our practical use of conductors. When we measure wire, we measure in a unit called gauge. In some places we might measure it by millimeters in diameter. In America we usually measure wire by gauge. The basic idea of wire gauge is we have an area and we see how many wires will fit inside that area. So the bigger the wire, the fewer will fit in. Now, the thing to remember about wire gauge is the smaller the number, the bigger the wire. For example, the diameter of 4 gauge wire is pretty close to 1/2 inch. But if we take a look at 10 gauge wire, we're looking at more like a little less than 1/8 of an inch. 30 gauge wire is less than 1 millimeter in diameter. So the higher the number, the smaller the wire. Now when it comes to conductivity, if you have a bigger diameter wire, it's going to carry more current or have less resistance than a smaller diameter wire. That makes a lot of sense. It's just like a hose. A garden hose cannot carry as much water as a fire hose. A garden hose will have more resistance to water flow than a fire hose does. So thicker wire has less resistance than thin wire. And likewise, if we have a longer wire, it has more resistance than a shorter wire. It may be a little counterintuitive, thinking, well, if it's the same diameter, shouldn't that make no difference? Have it as long as you want, and it should have the same resistance. But there's friction as the electricity goes through the wire, and so the further it has to go, the more resistance it has. That's the same thing that's true for a hose. If you have a long hose, it actually has more resistance than a short hose because of what's called pipe friction and other things that affect it, such as eddy currents. There's different things that affect water flow than affect electric flow. But there are things that slow down water flow where you make the pipe or the hose longer, you get more resistance. And the same thing with electricity. A longer wire has more resistance than a shorter wire. So a thick wire has less resistance than a thin wire. A long wire has more resistance than a short wire. And temperature has an effect too. As the temperature goes up, the resistance of a wire increases. So cooler wire has less resistance than warmer wire. And this has been known to have a significant effect on Ethernet cables or network cables, such as might be stored in a hot attic, actually increases the resistance of the wires enough to make a significant difference. So warmer wire has more resistance than colder wire. This also has a big effect in such things as incandescent light bulbs. As you turn on the power, the filament of the light bulb is cold, so there's a surge of current through it, but it heats up and that increases the resistance, so the current goes down, and we eventually get to a point where the dissipation of heat and the amount of current going through causing the heating hits a point of equilibrium, and the temperature and current will stabilize. The practical limit of how much current a wire can carry is called its ampacity, and that depends on what it's made of, what the temperature is, and what its diameter is. For example, a 10 gauge copper wire at room temperature can carry about 30 amps before it starts to heat up to the point where that heat is unacceptable. Now there's another class of materials we call superconductors. And superconductivity, actually any material will superconduct if you get its temperature low enough. So Certain materials, if you get them to a low enough temperature, they will go into a condition called superconduction. And essentially what we're saying is that at the superconducting temperature or below, the resistance becomes zero. This happens at about 4.2 kelvins for mercury, which is about minus 269 degrees Celsius. Niobium nitride superconducts at about 16 kelvins, a little higher temperature, or minus 257 degrees Celsius. Until about 1986, it was thought that nothing would superconduct at a temperature higher than 30 kelvins, but more recently we found many materials that will superconduct at higher temperatures. I believe the highest temperature for a superconductor we know today would be yttrium barium copper oxide, which superconducts at 77 kelvins, or minus 196 degrees centigrade. Now once again, superconductivity, we say that it has zero resistance. Take a quick look at Ohm's law. Let's see. Voltage over resistance equals current. And so if we have zero resistance, wouldn't we have infinite current? Well, if we had infinite current, that requires infinite electrons. So what does superconductivity really do for us? Well, when we hit that superconducting state, what that means is if we get the electrons moving at all, they will continue to move without any voltage being applied. So superconducting materials, when they're in a superconducting condition, will have a current flowing through them, even with no voltage. And we can see some demonstrations of this, such as pouring liquid oxygen on top of certain superconducting materials. If we put that on top of a magnet, when it starts to superconduct, the currents start to flow inside the superconducting material, causing a magnetic field, and they will levitate above the magnet. And so superconductors are looked at as ways to carry electricity very efficiently. And also we can make superconducting levitators. One thing we're thinking about is making trains that have superconductors in them that cause them to levitate off of a magnetic track. And so we can lift them up and have no friction without the cost of having any electricity in conventional electromagnets. So now we've talked about conductors, semiconductors a little bit, and superconductors. Let's talk for a moment about insulators. Now, normally we think of insulators as non-metals. So the metals are conductors, and most of the materials are metals. Then we get over to the right side of the periodic table, we get to the non-metals, which have so many electrons in their outer shells, 5 or more, that they are not conductors. Arsenic and antimony are a couple of exceptions that are metallic, even though they're on the right side of the table. But most of these materials are non-metallic and are considered non-conductors. But if you take a look at these materials, you'll find that they're not very practical for making insulators out of. In other words, we use insulators to separate conductors from each other. And our non-conductors tend to be either liquid or gaseous at standard temperatures and pressures. So even though you may have heard, oh yeah, these are our non-conductors, our insulators, well, they are not something we can make insulators out of. So most insulators are made out of ceramics. Ceramics tend to be metal oxides, such as our most common ceramic materials are aluminum oxides. Ceramic knives and other types of high-tech ceramics are made from zirconium oxides. So those are ceramics. Glasses, which are materials such as silicon oxides and germanium oxides, which you're familiar with the properties of glass. And many plastics, which are long chain polymers of usually hydrocarbons, also tend to make good insulators because they are solid at room temperature and they don't conduct electricity. Another good insulator is air, but like any insulator, if you get the voltage across it high enough, you will break down that insulation and it will conduct. You will finally force the electrons to be able to move. And air does this at a fairly low temperature, depending on how far apart the conductors are. And so if I remember right, about 10,000 volts will cause a column of air about as far apart as my fingers to start conducting. 500,000 volts will cause a column of about 10 feet across to start conducting. So it depends on how big the voltage is and how far apart the conductors are. So let's take a quick review. Conductors tend to be metals because metals have 3 or fewer electrons in their valence shells, and in a mass of metal, the electrons in the valence shell are free to float around inside the mass of metal, and we can make them move by putting a voltage on opposite ends, or a voltage difference on opposite ends of that mass of metal. The larger diameter a conductor is, the less resistance it has, or the more it will conduct. So thinner conductors have more resistance, larger conductors have less resistance. A short conductor has less resistance than a long conductor. So short diameter, long distance gives you more resistance. Large diameter, shorter distance or shorter length gives you less resistance. And as conductors heat up, they tend to increase their resistance. So temperature goes up, resistance goes up. Temperature goes down, resistance goes down. The ability of a conductor to carry current is called its ampacity. The ampacity is limited by the practical temperature rise that we get as we run current through it. An example of 10 gauge copper wire at room temperature has an ampacity of about 30 amps. Superconductors are materials that at low temperatures lose their resistance entirely. And so, although we can't have infinite current because that would require infinite electrons, if we get a material into a superconducting state, it will have electrical current with no voltage applied. But superconductors have to be cooled down. I believe the highest temperature superconductor is yttrium barium copper nitride, which superconducts at 77 degrees Kelvin or minus 196 degrees Celsius. There are rumors of room temperature superconductors being discovered, but none of these have been confirmed. It would be great if we found them, but none of them have been confirmed, just scientific rumors. Semiconductors are materials that have 4 electrons in their valence shell. These would be carbon, germanium, silicon, and tin, and lead. Although tin and lead are those materials that are actually more metallic than semiconductors, so they act as metals. So we have carbon and germanium and silicon, the most important of which being silicon. We'll talk about semiconductors at another time, but semiconductors form a covalent bond which actually binds the electrons in pretty strongly into the crystal lattice, and they're really not very good conductors at all. But we can put impurities into these crystals and control their conductivity and make the electronics that we have today, which are all made from semiconductor materials, almost always silicon. And last but not least, insulators are materials that do not conduct electricity. They have the electrons are bound into the crystal structure in such a way that it's very hard to give them enough energy to get them to move. Yes, you can. You put enough voltage across a insulator, you will get the electrons to move, but it takes a huge amount of voltage to do it. And so the nonmetals in the periodic table do not make good insulators because they are liquid or gaseous at room temperatures. So our insulators tend to be ceramics or glasses or plastics. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocademy.net, you can go to patreon.com/join/vocademy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.